Welcome to your first lesson of Physics 11. I'm excited to have you guys back for another year of physics. We're going to start out with a concept called momentum. And momentum can be thought of as the amount of motion that an object has. Or maybe another way to say it would be how hard it is to bring something to a stop or how hard it is to get something going. So one illustration that I like to think of is the difference between trying to stop a football player who's running full tilt or to stop a little 2-year-old who's running. So momentum depends a little bit on mass. It'd be a lot harder to stop that football player who's huge than it would be to stop your little 2-year-old brother. But it also depends on how fast they're going. A football player is a whole lot harder to stop if they're running full speed than if they're just kind of walking along. And the same thing for your little 2-year-old brother. It's a lot easier to stop if they're just kind of toddling along the ground. They might even fall over and stop themselves than it is if they're running full speed and you have to get in front of them to stop them. So momentum is the amount of motion that an object has, and you can kind of think about it as how hard it is to bring something to a stop. So that depends both on how fast it's going and on how much mass it has. It's how hard it is to stop. So it's example number 1 says, for each of the diagrams below, state whether the amount of motion is comparatively large or small. So the first one we've got going on here is a little ball. Think of this as your little 2-year-old brother. And it's not going very fast. So this would be pretty easy to catch. This would be amount of motion. This is pretty small amount of motion. And on the other end of the spectrum, think of this as your football player who's running full speed, a lot of mass, a lot of velocity. This is going to be a large amount of motion. Now, these ones in the middle are a little hard to compare because you'd have to actually put numbers on it. But in general, I would consider the football player harder to stop. Even if all they're doing is walking forward, they're still harder to stop than your little 2-year-old brother is running full tilt. If you can get in front of your brother and he runs right into you, he can't really move you much. But the football player, on the other hand, harder to stop. So we have a really small at this side. This is a little bit more. This is a little bit more than this one maybe. And this is the largest motion that we've got going on at this end. So again, depends both on mass and velocity, how hard something is to stop or how much motion that they have. And we call this the motion product. And there's the hint of how you're going to find it. Product, multiply. And we use the letter P for product. It's the motion product, but we're going to use the letter P because we already use M for mass in order to denote momentum. So momentum is a vector quantity. Remember from your past physics classes, this means it has a direction as well as a magnitude, and its direction is the same as the velocity vector. Whatever direction the object is moving in is the direction that its momentum is in. So here we can write the vector equation. Your momentum, P vector, is equal to your mass, M, times your velocity vector. So mass is a scalar, it can multiply a vector, no problem, and my direction is going to match with both of those. The units for momentum are going to be, well, mass is measured in kilograms, that's my base unit, and velocity is measured in meters per second, so we can say kilograms, meters per second. If you want, you can put a dot in between those to denote multiplication, or just write kilogram, meters per second. So we have our momentum, P, which is our motion product. Think P product, kilogram, meters per second, because mass is in kilograms and velocity is in meters per second. Note that a Newton second, an N times S, can also be used as a momentum unit. And this comes from the fact that my Newton, remember, we had last year force equals mass times acceleration. A Newton, my force, is equal to mass kilograms times acceleration meters per second squared. So if I have a Newton times a second, I end up with a Newton is a kilogram times meters per second squared times a second. Well, this second on top is going to cancel out with one of these seconds on the bottom, get rid of my squared, which leaves me with the units of kilogram meters per second, which is what I found for momentum. So later on, we're going to use this unit of Newton seconds more because we're actually going to also use force times time in calculating momentum. So just kind of a preview of what's coming up. Kilogram meter per second is the same as a Newton second. Example number 2. Estimate the momentum of a top pitcher's fastball, the momentum of a person and bicycle on a relaxed ride, and the momentum of a car driving on a city street. So we want to estimate their momentums, and before we estimate the momentums, we're just going to estimate mass and speed. So there's no exact answer for this, but just kind of thinking through estimate mass, speed, and from that we can calculate the estimated momentum. So in order to do that, we're going to say, okay, fastball, estimate the mass of a fastball, not too big, maybe a quarter kilo, so we'll say 0.25 kilograms. You might even be able to look that up on the internet if you wanted to. A top pitcher's fastball goes about 50 meters per second, pretty darn fast. And you multiply these together, so your mass times your speed is going to give you your estimated momentum. So 0.25 times 50 is going to give me 12.5 kilogram meters per second. Now if that hits you, that's going to hurt. 5 meter per second fastball that hurts you. Ouch! That would not be so fun. Now a bike and a rider. Let's say maybe my bike is about 30 kilos and my rider's 70 kilos, so total maybe around 100 kilos for my bike and my rider. And just relax, not going very fast. Let's say maybe 4 meters per second. And again, these are estimates, so it's kind of just ballparking it. And to find your estimated momentum, we have 100 times 4 would be 400 kilogram times meters per second. So fastball might hurt to get hit by. This is going to knock you over and maybe even result in injury. So not so fun to get hit by a biker. If he rolls over your foot, not great. If he crashes into you, you could end up with a broken leg. So more momentum for a bike and a rider than just a fastball, even though the fastball is moving a whole lot faster. Then we upgrade to a car, which you're looking at about 1,000 kilograms. It's another order of magnitude. And driving on a city street, well, let's say they're not going super fast, but maybe around 15 meters per second. I can actually go 15 meters per second on my bike, so that's not as fast as a car can go for sure. And then multiply those together, that gives us 15,000 kilogram meters per second. You get hit by this car, you are going to be maybe not living anymore. Rest in peace. Here's your gravestone. So car, even more momentum, estimate because of the mass. So that hopefully gives you a ballpark figure for what momentum is, how it feels like. The faster things are going, the harder it is to stop, and the more injury would be done to you if you got hit by it. A couple more examples before we wrap up this lesson. A baseball of mass 0.14 kilograms is moving at 35 meters per second. Find the momentum of the baseball. So if you remember, we did this last year, DFIC, write down your data, write down your formula, insert your numbers, and calculate. So my data in this case is going to be mass 0.14 kilograms and velocity, although no direction, so speed 35 meters per second. Formula, I'm looking for momentum. That's my P formula. P equals M times V. P equals M times V. Insert my numbers. Mass of 0.14 times speed of 35. And if you plug that into your calculator, multiply those together, I'm sure you can figure that out. It is 4.9 kilogram times meters per second. There's my final answer. So again, practice using DFIC. You don't have to write the DFIC every single time if you don't want to, but you do need to write down the information for each of those steps to show your work. So part B then asks you, find the velocity at which a bowling ball with a mass of 7.26 would have the same momentum as the baseball. So we calculate our momentum up here. We're going to use the same momentum, different mass. We want to find the velocity. So again, D for data. What do we know? Well, we know we have a mass of 7.26 kilograms. We know we have a momentum that is the same from the previous question, so my P is 4.9 kilograms meters per second. Remember to watch out if things are in base units or not. If these are not in base units, you need to practice some unit conversion. But fortunately, everything so far has been in base units. Pull out your formula, which we're looking at again, P equals mv. Now remember, in the formula section, before you start plugging in your numbers, you need to rearrange it to find what you're looking for. So in this case, we're looking for what is velocity. So you're going to rearrange this to find your velocity. In order to do that, divide both sides by m and write v equals p over m. So this is part of your formula section. You do need to show this rearranged formula. Now if it's simple enough and you want to write down the rearranged formula right off the bat, start with this. That is fine, but you do need to plug your numbers into the rearranged formula, not the original formula. So then we're going to go insert, plug in P equals 4.9 and mass is 7.26. And again, pull out your calculator, type in the numbers, 4.9 divided by 7.26. You can definitely do that. Gives you 0.675 meters per second. Now remember, we're writing all our answers for 2 to 3 sig figs. So 4.9, any numbers that are non-zero are automatically sig figs, so this is 2 sig figs. Any number that is a 0, zeros to the left don't count, so this is a 0 to the left. Zeros to the right, any zeros off of here count if your number has a decimal place. And zeros in the middle, if there had been a 0 in the middle, they do count. So this 0 does not count, and I have 1, 2, 3 sig figs. Hopefully that comes back to you pretty quickly. We did lots of sig figs last year. 2 or 3 sig figs for your answers. One more example says a 12 kilogram rock is dropped from a 75 meter high cliff. What is its momentum upon impact? So what information do we have? This is going to require you to remember some kinematics from last year. So we've got data, mass is 12 kilos, 12 kilograms. Drop from a height of 75 meters, 75 meter high cliff. So it's going to fall 75 meters. In other words, the distance, it's going to go negative 75 meters or 75 meters down. And what is its momentum upon impact? We're looking for what is momentum. So at first it might look like, well, I don't have enough information to figure this out. So there's a little bit more implicit information hidden in the question. First off is the fact that it is dropped. If you remember, that means that my V initial was 0 meters per second. But I don't want to find its initial momentum. I want to find its momentum upon impact. In other words, its final momentum, or using V final. So I need to be able to calculate V final. And the other information that I know, assuming that I am on Earth, is that my acceleration due to gravity is negative 9.8 meters per second squared. 9.8 meters per second squared. Downward, I'm going to use a negative 9.8. So in order to find my momentum upon impact, I'm first going to need to find my V final. You remember how that works? So look up a formula in your formula sheet that has D, V initial, V final, and A. And that formula is V final squared equals V initial squared plus 2AD. And in order to solve for V final, all I have to do is take the square root. So I'm just going to show that here, square root. And remember, this could be plus or minus. Whenever you take a square root, don't forget that plus or minus. Then I'm going to insert into that formula the information that I have. So I've got my B initial to be 0 plus 2 times negative 9.8 times negative 75. Plug that into my calculator. So there, I've got it. And in my calculator, I need to include these parentheses to make sure I'm taking the square root of everything. If I don't include the parentheses, it only takes the square root of 0. So there I've got 38.34057 whatever. And I'm going to keep a few extra decimals when I write down my answer, just so that I don't end up with rounding errors at the end. Remember, we don't like rounding errors. So I'm going to write down 38 point, I think I'm going to go 3405. Oops, that kind of went off the screen. Sorry about that. Let me see if I can resize that. 3, 4. What am I looking at? Yep. Move it over a bit. There we go. 3405. Oh, wrong way. There, got it. 3405 that I'm going to use in my next calculation then. So next, I'm going to do my momentum calculation using V final. So my momentum on impact final equals mv final. My mass was 12 times that, 38.3405. And on my calculator, I'm not actually even going to type in this 3.045. I'm going to go 12 times second answer. So I'm pulling all the decimals. I'm not even going to round at all. So that gives me an unrounded number, and then I can take that number and use that. Now, one thing actually I forgot earlier is this is a negative 38 because it's going downward. So I can put negative 38 is going to give me a negative 460 kilogram meters per second square, sorry, meters per second. And I can also write this or 460 kilogram meters per second down. Give me a sec. I'm gonna go back. Yep. Didn't realize my scaling was so off when I put my calculator up there. That's okay. There you have it. Meters per second downward. So you can put it in as a negative for your direction, or you can put the down for your direction. Don't put both because negative up is down. But there you've got the idea. All right, that's it for this lesson. Good luck with your homework and your mastery quiz.